A linear congruence equation is an equation of this form. So ax congruent with b modulo n. And here a and b are constants and x is an unknown. So all of these are of course integers. So let's take an example. So for example 3x congruent with 2 in modulo 5. So what are the solutions to this linear congruence equation? Well, then you can use, for example, you can just test numbers here, but we can also use this clock to visualize. So then we have 0, 1, 2, 3, and 4. So this is modulo 5. And then we're looking for numbers that we take 3 times x equals to 2. So if x is 0, we get 0, so we start here. And then x is the number of steps we want to take. We can think of this as a number of steps we want to take. And each step constitutes we're taking 3, a step with length 3. Okay, so we take one step, then we end up here. Or we could just draw it like this. So we end up here. So 1, 2, 3. If you take 2 steps, so 2 times 3, then we take one step more, so we get 1, 2, 3. Then we end up here. So now we will see when we end up at 2, because then we know what x must be. So take one step more, so 1, 2, 3, then we end up here. So this is 1 step, 2 steps, 3 steps. And if we now take one more step, so 1, 2, 3, we end up at 2. So after 4 steps, we end up at 2. That means we have found the solution. So we see that taking x 4 steps is the solution. Are there more solutions? Okay, so we take one more step from here now, 1, 2, 3, we end up at the starting point. Okay, so after 5 steps, we end up at the starting point. So then things just repeat. So that means that after 5 steps, we go back to the starting point. So if 4 is the solution, then 4 plus 5 is the solution. So 9, and then 9 plus 5 is 14. So all multiples of 5 added to 4, or subtracted if you want to go in the opposite direction. However, all the numbers for 4 plus a multiple of 5, that's already covered by, since it's modulo 5. So for example, if we say that 9 is the solution, then we know that 9 is congruent with 4, modulo 5. So we have already found all the solutions we need here to 4. So we only need to check the numbers really x equal to 0, 1, 2, 3, and 4. Because 5, that's the same thing as 0 in modulo 5. So when we're working modulo 5, we only have to check numbers 0, 1, 2, 3, 4, the smaller than the base. Not the base, but the modulo. So we only have to check those. So that means that after you have checked 0, 1, 2, 3, 4, then we have checked all we need to check. So the rest are just multiples of 5 then. For example, now we know that 4 was the solution. So all multiples added or subtracted to 4 or 5 will also be solutions. We could also, instead of visualizing here, even simply just to test all the possibilities. If this would be a normal equation, then it's hard to test all possibilities because there could be infinite many. But in this case we have integers, and we only have integers smaller than 5. So we can test all. So we could just explicitly test all of the possibilities. So if you test 0, 3 times 0, well, that's 0. So that is not congruent with 2. And if we put in x equal to 1, then we get 3, and that's not congruent with 2, so that's not the solution. So 3 times 2, that's 6, and 6 is congruent with 1 in model 5, and that's not congruent with 2, so not the solution. 3 times 3, well, that's 9. 9 is congruent with 4, which is not congruent with 2. And then 3 times 4, that's 12, and that's congruent with 2 in model 5. And this is, of course, congruent with 2. So here we have a solution. Or rather, this is the solution. And then we don't need to test anymore, because 5, for example, that's the same as 0 in model 5. Also, we don't need to test in the negative side, -1. That's the same as a 4 in model 5. So we only need to test these. And then we have found all solutions. So all solutions to this equation are these. Let's take another example. So if we have 4x congruent with b, and b here is some constant, modulo 12. For which number of b, does this equation have a solution? Okay, so how can we find that? Let's visualize with our clock here. Since it's model 12, we have our normal clock. So we have 0, 3, 6, 9, and all the other values. So this is model 12. Then we want to find out if we start here and take a number of steps, x steps, with the step length of 4. When do we end up at b? Okay, we don't know what b is now, but then we can find out what b must be if this should have the solution. So let us just try here now. If you take 0 steps, then we start here. Take 1 step, then we end up here. We take a step length of 4, so 1, 2, 3, 4. Okay, so this is x equal to 1 step. And then we take 1 step more, 1, 2, 3, 4, we end up there. And if you take 1 more, then we come back at the starting point. So we see that only if b is equal to 0, 4, or 8 does this equation have any solutions, because we can never reach the other numbers. So we see that for this to have a solution, b must be congruent to 0, or 4, or 8. So for these, it has a solution, but for the others, it doesn't. One reason studying linear congruence equations, other than it's part of studying modular arithmetic, is also because you can't handle linear congruence equations in the same way as normal equations. So it teaches you that you have to be careful on what you are studying. And so the rules of solving an equations are not obvious if you don't have normal equations. To show that, let's look at the following equation. So let's say that we want to find solutions to this one. Here it's easy just to test. We test numbers 0, 1, 2, 3 up to 11 to see what is a solution. If we do that, then we'll find out that 3 is the only solution. So 7 times 3 is 21, and 21 is congruent with 9 modulo 12. And that's the only solution if you test. Let's now say that we start with this and we multiply both sides by 2. So we multiply this, both sides by 2, as we could do in a normal equation. What happens then? Then we have 14x, and this is 18. 14 is now the same thing as 2 modulo 12. And 18 is the same thing as 6 in modulo 12. Okay, so what numbers are solutions to this equation? Then again, you can just test. And if you test this for solutions, you will find out that still 3 is a solution, but also 9 is a solution. So suddenly, just by multiplying both sides with 2, you get another solution. That means that these two equations, this one and this one, are not congruent, not equivalent. So that means that they don't have the same solutions. So if you would have done this with normal equation, for the normal numbers, not modular, then of course it would have the same solutions, but here it doesn't. So you can't just multiply a number on both sides and expect it to have the same solutions. Okay, so what's the reason for that? Why does this happen from modular arithmetic? Okay, so let's look a little bit in more to detail why this happens. Let's take the first one. What does this mean to find solutions to this equation? It means that 7x should differ from 9 with the multiple of 12. So that is what it really means. And now we shouldn't have congruence here, but real equality sign. So this is the same thing as this, that 7x differs from 9 on the multiple of 12. Okay, if you now look at the other equation here now, we had multiplied by 2 on both sides. What does this correspond to? Okay, that corresponds to that 2 times 7x should differ from this with the multiple of 12. Okay, so these should differ multiple of 12. If you now compare these two, we see that there is a difference here now. We see that we have multiplied 7x and 9, but we haven't multiplied this. So if we take this as an equation, then we multiply that with 2 on both sides, and that is of course allowed since it's a normal equation. So if you multiply both sides by 2, then you get this. And now we see that there's a difference between this one and this one. You see, these are identical, but here is a difference, because that one is multiplied by 2, and this is not. So that's the reason for we are getting new solutions, because when we multiply both sides with 2 here, then we didn't multiply by 12, and that's the reason for it, we are coming up with new solutions. So if you look at this equation, this one is equivalent to this one, because we haven't done anything strange here. And this one, you can go back and write as a congruence equation. Since we have 12 times 2 now, this is 24. So we see that when we multiply both sides by 2, then we should also multiply the modular 12. And that we didn't do when we multiplied both sides. So we haven't treated the equation correctly. And that's why the reason we came up with new solutions suddenly. Because this one is the one that's identical or equivalent to this one, not that one here. So this equation here is equivalent with this one. So that is an allowed. If you multiply 2 all over, also the modulo, then we can multiply on both sides, but not if we skip this. So the rules for manipulating linear congruence equations like this. Then you have to treat this as it is not exactly a normal equation. However, you are allowed to add or subtract any number on both sides. So that's like a normal equation. You can add and subtract on both sides, and you don't have to add a modulo. However, if you multiply with the same number not equal to 0, then you also have to multiply the modular. So you can multiply both sides, but then also have to multiply this. And for example, if you have 6x and here you have 4 modulo 12, you can also divide on both sides if it's not equal to 0. You can divide on both sides if all these three, including the modulo, are divisible by that number. So we can divide by 2, but then we also have to divide here. So this is equivalent to this one. Okay, so let's take some examples. We want to solve the following equation. So apart from it is modular arithmetic, this looks like a normal linear equation. Okay, so now we are allowed to add the same thing on both sides. So we can add, for example, 3x on both sides. And then we don't have to do anything with the modulo. We see here, this is 5x. And this cancels that. So we have this. Then we can subtract with 2 on both sides. Okay, so let's do that a little bit faster this time. So minus 2 here, that cancels. 4 minus 2, that's 2. So we end up with this equation. So this one is equivalent with this one. And now we can just do what we did before. We can just test. We test 0, 1, 2, 3, 4, 5, 6. And if we do that, we will find out that the only possible solution, or the only solution is 6 modulo 7. So it means that 6, and then also 6 plus 7, 6 plus 14, or minus 7 are also solutions. But this is the only solution, modulo 7. Now we want to confirm what we did earlier, that if you can multiply both sides with the number if you multiply the modulo at the same time. So let's take an explicit example here, a concrete example. So we take this one. Okay, what solutions does this have? Then we can just solve it. Then we have this. And what's that? If we check now for solutions, then we'll find that the only solutions to this one is x equal to 4 modulo 5. And let me just write it down what that this means if we write explicitly all the numbers. So 4 is a solution, but also all the multiples of 5, so also 9, 14, and so on. And if you go the other direction, also minus 1, minus 6, and so on. Okay, so these are the solutions to that equation. Let's say now that we want to multiply both sides with some number not equal to 0. So let's just pick, for example, 3. So we multiply both sides with 3. And then we know that we should multiply also the modulo with 3. And if we multiply in here, we end up with 6x plus 3 and 12. And this becomes modulo 15 now. Okay, and this we can write as 6x and 9 modulo 15. What are the solutions now to this one? Okay, if you just check here now for all the possibilities between 0 and 15, then you will see that the solutions are 4 and 9 and also 14. And remember now this is modulo 15. Okay, so now it seems like we have suddenly gotten more solutions, not just this one. But that's not correct, because if you analyze a little bit more in detail, we'll see that we have gotten the same solutions. So it was okay to multiply both sides, since we multiply also the modulo. Because which numbers are these? These numbers are 4, of course. Then all multiples of 15, so 19 for example. And then we have 34. And if you go the other direction, we have minus 11 and minus 26. And if you do similar here for these, so we have 9, adding all multiples of 15, so 24, 39, and so on. And if you take minus, so minus 6, minus 21, and finally this one, so we have 14, adding multiples of 15, so 29, and then we have 44, minus 1, minus 16. Okay, so those solutions are really easy if you write them in numbers. But if you compare this one with this one, you will see that these contain exactly the same numbers. So here is 4, 9, 14. Here is 4, 9, 14. Then the next one is 19. And that actually, we didn't write that here, but that will be the next number here. So we take these together, it will cover the same. And here's minus 1, minus 6. And the next one will be, of course, minus 11, since it's modulo 5. And the same here. We have also the same numbers here. Minus 11, minus 6, minus 1. So these two actually are the same solutions, even if it maybe not looked like that written like this. But that's because this contains more numbers. So 4 modulo 5 contains more numbers than these 3 and modulo 15, but it's the same solutions. These are the same solutions, even if superficially look different. Let us also check this for division. So let's take a concrete example. This one, for example. Here we see we have 2, 2, and 2 in all of these 3 parts of the equation. So now we know that we can divide by 2. So if we divide also the modulo, since all are divisible by 2. So we can divide by 2 here, that by 2, and this by 2. And then we see that we have gotten the solutions directly. So let's say that you don't trust this method of dividing all 3, that it gives you correct solutions. So let's take the original equation and let's not divide it by 2 all over, and see if that will give us the same solutions as that one. If you test now for solutions here, what solutions will you find? You will find that 2 and 5 are solutions, modulo 6. Is this the same as that? Are these two together the same as that one? Yes, they actually are, because if you write them out explicitly, this is 2 added multiples of 3. This is 5, 8, 11, and so on. And in the other direction, minus 1, minus 4, minus 7, and so on. What do we have here? Here we have 2, and then we have modulo 6. And then adding 6, that's 8. And the next one is 14, so on. Minus 6, that's minus 4, minus 10, and so on. And here we should start instead at 5, then adding modulo 6 with 11, 17, and minus 1, minus 7, and so on. However, if you now compare this one with these two taken together, you will see that they contain exactly the same numbers: 2, 5, 8, 11, 2, 5, 8, 11, and then minus 1, minus 4, minus 7, minus 1, minus 4, minus 7. So they contain exactly the same numbers. So it is okay to, if you have an equation, to divide by both sides if you also divide the modulo. But all of them have to be divisible by that number you divided with. So for example, all of them are divisible by 2. So we can divide by 2, including the modulo, as we did here. There are even more differences between linear equations and normal equations than this. And to see that, we will look now at this theorem. And the following theorem gives us another option of solving linear congruence equation. If you have that the greatest common divisor of two numbers k and n are equal to 1, then this equation here so here we have a linear congruence equation. This equation has the same solutions as this one. So these two have the same equation, if this is the case. So we can multiply a number on both sides of an equation and not multiply it in the modular if the greatest common divisor with the number we multiply and the modular is 1. So this is the special case from what I had before. Normally we said that if we multiply with k here, we should also multiply this by k. But we don't have to multiply that with the number if the number here we multiply by with and the modular, the greatest common divisor of these two is 1. So let's take an example of that. We will only take an example. We will not prove this one because it has to do with something called multiplicative inverses. So we will not do that here, but you can prove it is to be true. Okay, so let's take this one. 6x congruent with 8 modulo 9. Here we have that 6 and 8 are both divisible by 2. But modulo 9 is not divisible by 2. So we have that the greatest common divisor of 2 and 9 is 1. Okay, so in what way does that help us? Now, if you look at this equation here, we can write this as 2 times 3x. This as 2 times 4. Here we are not multiplying both sides, we're just rewriting 6 like this and 8 like this. So this equation is exactly the same as this one. Okay, but according now to this theorem here, you see if you have a number multiplying both sides here, and this number has the greatest common divisor with this one with 1, then it's the same solution as this one. So we can just drop this k here, since if it has greatest common divisor with this equal to 1. This number here corresponds to that k. Does this have a greatest common divisor with 9 equal to 1? Yes, it does. Because the greatest common divisor here is 1, you can easily check. That means that we can just drop it. We can drop the 2. And we don't change the modular. So this is according to the theorem on the previous page. And now we can just solve this in a normal fashion. And if you try to solve this, you will see that it lacks solutions. In this case, it just happened to be like that. This lacks solutions. So this lacks solutions, and that means that also this lacks solutions because they are equivalent. Even though we have studied here now linear congruence equation, it seems like this have nothing to do with Diophantine equations. But actually we now show that this is very closely related. It's doing actually the same thing. So solving linear congruence equations, same thing as solving Diophantine equations. So let's show that now here. So let's start with some linear congruence equation. So we take this one. Okay, what does this really mean? It means that ax and b are separated by a multiple of n. So now this is a normal equation. Let us rewrite this equation in the following way. So ax minus kn equals to b. And this we can rewrite as ax plus n times minus k equal to b. Okay, let's compare this with the Diophantine equation. The Diophantine equation we have like this. If we compare these two, we will see that they have the same structure. All the numbers here are integers. So we have a constant multiplying an unknown. Here is another constant multiplying. If we consider this to be the unknown, minus k, we could just call it y, for example. So this corresponds to y, and this corresponds to each other here on this side. So if you just identify it straight over, you will see that a linear congruence equation corresponds to a Diophantine equation in this way. So solving linear congruence equations, we could just as well solve Diophantine equations.